Okay, we're going to do the notes for 7.5. We're going to add some identities to our repertoire here. These are the sum and difference identities. So why do we need the sum and difference identities? Well, it's to be able to find sines, cosines, all the trig functions of values that are not on your unit circle, of course, without using a calculator. So for example, if I wanted to find the cosine of 15 degrees, well, that is not one of our special angles, 30, 60, 45, all of those angles. But I could rewrite 15 degrees as 45 degrees minus 30 degrees. And those are two of our special angles on our unit circle. So that is what we are going to do. Well, to be able to do this, you are going to need your sum and difference identities. So if you go back down towards the bottom, you can see that here is the sum identity for finding the cosine of an angle. And here's the cosine identity for finding the cosine of an angle. So here you have the difference and here you have the sum. Okay. So I will tell you, in a normal class where we're in class, I would usually give the students, I don't give them the Pythagorean identities, any of the identities we've had before, but starting here, I will always give them the sum and difference identities, and when we do the next two identities, I give those. So just so you know that, okay? So let's use these. So here we go. It says use the, we're going to go back to the first example, and we're actually going to find the cosine of 15 degrees using the sum and difference. So here's how we're going to do it. We're going to make 15 degrees into 45 degrees minus 30 degrees. And by the way, this is not the only way to do it. For example, if I did 60 minus 45, that would also give me 15 degrees. We should end up with the same answer in the end. So this is my alpha and this is my beta when I use this identity right here. So this is going to be the cosine of 45 degrees times the cosine of 30 degrees plus, so I'm just following the second identity, the sine of 45 degrees times the sine of 30 degrees. So once you have that, it's really just simply plug and chug. Well, what is the cosine of 45 degrees? That's root 2 over 2 times, what's the cosine of 30 degrees? This is all unit circle work. These are exact values. That's root 3 over 2 plus the sine of 45 degrees is root 2 over 2 times the sine of 30 degrees is 1/2. So when I multiply, I get root 6 over 4 plus root 2 over 4, the exact value, again, not plugging it into the calculator and getting an approximate value because it's rounded, for the cosine of 15 degrees is root 6 plus root 2 all over 4. And that's all there is to it. So it's literally a plug and chug. So let's go backwards for this example. It says the sum and difference formula can all be used also in reverse. For example, find the exact value of this expression right here. Well, you have to go back to your sum and difference and figure out which one it follows. Well, I know my alpha is 40 and my beta is 80, so that's helpful because those are my two angles. So if I go back and look at my identities, I will see that when the two expressions are being subtracted, it comes from the sum identity. So it's actually the cosine of 40 plus 80, which is the cosine of 120 degrees. And hopefully you know the cosine of 120 degrees is negative 1/2. So you can use those identities backwards. Just so identify your alpha and your beta. You know its cosine, and then just figure out and know that if this is being subtracted, it means that it was a sum to begin with. How about find the exact value of the cosine of pi halves minus theta? So again, this is my alpha, this is my beta, and I'm going to just plug it into my cosine, or difference, in this case, identity. So it'll be cosine pi halves cosine theta plus sine pi halves sine theta. Well, what's the cosine of pi halves? Hopefully you know that's 0. And the sine of pi halves is 1. So that would be 0 plus sine theta, which is simply sine theta. So that's what they're looking for there. Okay, so those are your cosine sum and difference identities. Now let's look at your sine sum and difference identities. So here you can see if I want the sine of two angles being added together, it's the sine of the first times the cosine of the second plus the cosine of the first times the sine of the second. Then you can see this one down here. Okay, so here we go. Now this is going to be a little bit more difficult because notice we're in pi radians here. So we have to figure out, now this is fairly big, so I'm going to assume that I need to figure out two angles that add up to be 19 pi over 12. So that's really hard. So what I will usually do if I'm doing this to try to find the angles is I'm just going to choose an angle. So let's see. Here's my thought process. Well, I know the common denominator has to be 12. So I'm going to choose an angle where there's a 4 on the bottom. So I could choose pi fourths, but pi fourths is pretty small. It is in the first quadrant. I'm going to choose the 3 pi fourths because I know 3 pi fourths is in the second quadrant. So my guess is that I'm going to use 3 pi fourths. Now, how am I going to figure out the other angle? Well, I'm going to take 19 pi over 12 and subtract 3 pi fourths, and I'm going to hope that I'm going to get one of my special angles. Well, that would be 19 pi over 12 minus, if I get a common denominator, this is going to be 9 pi over 12. Which gives me 10 pi over 12, which reduces to 5 pi 6, which is one of our special angles. So what I just figured out is that if I add 5 pi 6 and 3 pi fourths, I'm going to get 19 pi over 12. Are those the only two angles? Probably not, but those are the two that I'm going to use. So I'm going to find the sine of 19 pi over 12 by doing the sine of 3 pi fourths plus 5 pi 6. So again, this is my alpha, this is my beta. I'm going to plug it into my sine sum identity here. So it'd be sine of 3 pi fourths cosine of 5 pi 6 plus cosine of 3 pi fourths sine of 5 pi 6. Okay, so once I've written that out, it's just plugging in our values. So the sine of 3 pi fourths is root 2 over 2. It's positive. It's in the second quadrant. The cosine of 5 pi 6 is negative root 3 over 2. These are all unit circle values. The cosine of 3 pi fourths is negative root 2 over 2. And the sine of 5 pi 6 is positive 1/2. So this would be negative root 6 over 4 minus root 2 over 4, which would simply be negative, root 6 minus root 2, sorry about that, all over 4. So that again is the exact value of the sine of 19 pi 12ths. And again, you may have chosen or figured out two other angles that add up to be 19 pi over 12. That's fine. Okay, so example 5, we're still going to be using our sum and difference identities. So what we're going to do, because you'll notice that these are not unit circle values, is we're going to set up two triangles. We're going to have an alpha triangle, and we're going to have a beta triangle, because notice this is the sine of alpha is 3/5, and this one is the sine of beta is negative root 5 over 5. So it says our alpha is between pi halves and pi. So that tells me I'm in the second quadrant. We've done something like this before. So if the sine is 3/5, that's the 3, that's the 5. Pythagorean theorem tells you that's 4, but of course it's going to be negative, because notice you have to go to the left to get that. Don't forget about your signs. Be careful. Our beta triangle, it says, is between 3 pi halves and 2 pi. So we're talking fourth quadrant. And our beta is negative, or our sine of beta is negative 1 over root 5. And again, sine is opposite over hypotenuse. So I'm going to put the negative 1 there. I'm going to put the root 5 there. And then if I do my Pythagorean theorem, let's see, that'd be 5 minus, I think this is going to be positive 2. All right, so I have alpha triangle, I have beta triangle. So look, we are given the sine of alpha is 3/5. Look at your triangle, what's the cosine of alpha? Well, the cosine of alpha is going to simply be adjacent over hypotenuse. That is going to be negative 4/5. We're given the sine of beta. It's asking me for the cosine of beta. Same thing. Here's my angle. The cosine would be adjacent over hypotenuse. So that would be 2 over root 5. If I get the radical out of the basement, it's going to be 2 root 5 over 5. So now they're asking for what is the cosine of alpha plus beta. Well, let's just quickly write down our identity for cosine so we remember it. So remember that it's cosine alpha, cosine beta, minus sine alpha, sine beta. So that's just the identity. I'm just writing it down. So the cosine of alpha is negative 4/5 times the cosine of beta is 2 root 5 over 5 minus the sine of alpha is 3/5 times the sine of beta is negative root 5 over 5. So I'm just plugging in the values from the triangles that I already have. So this is going to be negative 8 root 5 over 25 minus a negative is going to end up to be plus 3 root 5 over 25, which is negative 5 root 5 over 25. And then just quickly to simplify, I can cancel the 5's out. So it's going to be negative 1 root 5 over 5. And there you go. Let's do the same thing, but this time we're going to find the sine of alpha plus beta. So again, notice we're not actually finding alpha and beta. We don't even care what the angles are. We're just finding values. So if I use my sine identity, it would be sine alpha cosine beta plus cosine alpha sine beta. All right, so here we go. What's the sine of alpha? Well, we know that's 3/5 times the cosine of beta is 2 root 5 over 5 plus the cosine of alpha is negative 4/5 times the sine of beta is negative root 5 over 5. So I just plugged in my values. So this would be 6 root 5 over 25 plus positive 4 root 5 over 25. Adding them, you get 10 root 5 over 25. I can cancel a 5 out of there, and I'm going to get 2 root 5 over 5. And there you go. All right, last ones we're going to do are the tangents, and the tangents can get a little ugly with the algebra. I'm going to do that in a part 3 because I'm already up to 15 minutes here.